Welcome back. Let us return to Richard Byrd. In the next two videos, we will explore his 1989 paper titled Algebraic Identities for Program Calculation. In this paper, Byrd derives efficient implementations for two problems: min-max and the maximum segment sum. In this episode, we will focus on the min-max part of the paper. To really understand Byrd's derivation, we will do a deep dive into the alpha-beta pruning algorithm and its variations. We will also take a short detour into lattice theory and De Morgan algebras. And to make things concrete, we will look at how Stockfish analyzes a real chess position. Let us go over the laws that Byrd introduces in the paper, in the order in which they appear. The first one is called map distributivity. It says the following: if we apply the function g to every element of a list, and then apply f to every element of that result, we get the same outcome as applying f composed with g directly to the original list. In other words, mapping g and then mapping f is the same as mapping their composition. We do not need to prove this law ourselves. The standard library already provides an equivalent statement. Let us look at the next law that appears in Byrd's paper. This one is called the first duality theorem. It states the following: if the operator is associative, and if it has an identity element A, then a left fold and a right fold produce the same result. An associative binary operator with an identity element is a monoid. In Agda, we can use the is-monoid structure from the standard library to capture this assumption. The proof is straightforward. We proceed by induction on the list. In the empty list case, both folds evaluate to the identity element. So the proof is simple reflection. The non-empty case is also simple. We begin by expanding the definition of the left fold. We then use the identity law of the monoid to reduce f applied to epsilon and x down to x. After that, we rely on a helper lemma. That allows us to rewrite the accumulator form of the fold. This gives us the structure we need to make the inductive call to the same theorem. And that completes the proof. The next law is called map promotion. It states that if we first concatenate a list of lists and then apply the function f to every element, we get the same result as first applying map f to each component list and then concatenating the outcomes. In other words, mapping f inside each sublist and then flattening the structure is equivalent to flattening first and mapping afterwards. We do not need to prove this law ourselves. The Agda standard library already provides a proof for it. The next law has a very similar shape. It is called fold promotion. It says the following: if f is an associative operator with an identity element epsilon, then when we want to fold a list of lists, we can do it in two equivalent ways. We can first concatenate all the lists and then apply the fold. Or we can first fold each individual list and then fold the resulting list of values. Both approaches produce the same result. The proof is simple. We proceed by induction on the list of lists. The empty case is straightforward. Both sides evaluate to the identity element. For the non-empty case, we begin by expanding the definition of concat. We then use a lemma from the standard library to rewrite the left fold over an appended list. After that, we apply our helper lemma to move the accumulator into the right shape. At this point, the structure matches the inductive hypothesis, so we recursively call the same theorem on the shorter list. Once that rewrite is complete, we use our helper lemma again, followed by the identity law of the monoid. That gives us the right-hand side we want. The final law in this sequence is called fold map fusion. It says that instead of first applying the function f to every element of a list, and then folding the result with a binary operator, g, we can fold directly using a modified operator. This modified operator incorporates the fact that f must be applied to the right argument. In other words, we do not need two passes over the list. A single fold is enough, as long as we adjust the operator appropriately. This law is already available in the Agda standard library under the name fold map. Now that we have stocked our Agda toolbox with these identities, we can see how Bird tackles the min-max problem. On the screen, we see his definition of min-max. First, min defined as a left fold on the list, using the down operator with positive infinity as the seed. Bird relies on Bird-Mertens formalism. The down operator is similar to the min in the C++ standard library. It takes two numbers and returns the smaller one. Similarly, max is defined as a left fold on the list using the up operator with negative infinity as the seed. The up operator is similar to the max function in the C++ standard library. It takes two numbers and returns the bigger one. With these definitions in place, min-max is defined by first mapping each list with max and then applying min to the resulting list of values. This gives us the specification that Bird starts from in his derivation. To work with positive and negative infinity in Agda, we introduce a small custom data type. On the screen, we see a type with three constructors. One for negative infinity, one for positive infinity, and one called fin, which wraps an ordinary integer to represent all finite values. This gives us a simple and precise way to extend the integers with the two infinities we need. For min-max and alpha-beta pruning, we can now define the up and down operators on this extended integer type. These definitions are straightforward. When both arguments are finite, the operators simply rely on the corresponding minimum and maximum functions from the standard library. In all other cases, we use the basic facts about infinities. Negative infinity is smaller than everything. Positive infinity is larger than everything. Listeners should convince themselves of two things. First, that up forms a monoid, with negative infinity as the identity element. And second, that down forms a monoid, with positive infinity as the identity. The link to the full code is available in the description, including the proofs of these properties. Bird then introduces a new binary operator. It takes a number and a list of numbers. It compares the given number with the maximum of the list and returns whichever of the two is smaller. Bird also introduces a ternary operator. It takes three numbers as input. Its job is to clamp the first number between the other two. If the first argument lies between the second and the third, we simply get it back. If it is smaller than the lower bound, we return the lower bound. And if it is larger than the upper bound, we return the upper bound. This operator will later appear in the algebraic formulation of alpha-beta pruning. Here's a crucial lemma that links the two operators we just defined. For a given number, x, and a list of numbers, applying the binary operator .circle to them is the same as folding the clamp operator over the list using negative infinity as the seed. The proof takes only 3 steps. We start by using a helper lemma to expand the definition of the .circle operator and to pull the max outside. Next, we replace max by its definition, and finally, we apply the fold map fusion law that we saw earlier. That gets us to the right-hand side. Now we come to a lemma that reduces min-max to a single left fold. Given a list of numbers, the min-max of that structure is the same as left folding the list of lists with the dot circle operator using positive infinity as the seed. The proof is essentially one step. We apply the fold map fusion law that we introduced earlier. Once that rewrite is done, the two sides are identical. Bird then goes one step further and introduces the notion of a left zero. He observes that the up and down operators absorb each other. Given any pair of numbers, x and y, the maximum of x and the minimum of x and y is always just x. The proof goes by simple pattern matching. In every case, the result is self-evident. This absorption law is then used to show that for any number x, clamping x with any upper bound u always returns x. Bird calls this a left zero. The idea is important. During a fold, if the accumulator ever reaches this left zero state, the computation can short circuit. No further work is needed because the result will not change. Bird now introduces a fast left fold. It behaves like a normal left fold, but it bails out early the moment a decidable predicate succeeds. This lets us exploit the left zero property. If the accumulator ever reaches a value that guarantees the rest of the computation is irrelevant, the fold stops immediately. With this in place, our dot circle operator can be rewritten using this fast fold. In our case, the decidable predicate simply checks whether the accumulator has reached the first argument. This gives us a direct and efficient formulation of the alpha-beta step. We now arrive at Bird's efficient formulation of the alpha-beta algorithm. Alpha-beta is defined as a left fold using the new operator alpha-beta with positive infinity as the seed. This captures the pruning behavior directly. To prove correctness, we rely on the min-max lemma we established earlier. That lemma reduces min-max to a single left fold with the dot circle operator. From there, we apply fold-o-kong from the standard library to rewrite the fold so that it uses our av operator instead. Once that substitution is made, we get the required right-hand side. The full code is linked in the description. It includes additional proofs about the fast left fold and the helper lemmas we have used throughout. Bird asserts that this function captures the essence of the alpha-beta algorithm. To verify that claim, we now pause our algebraic journey and turn to the algorithm itself. The literature around alpha-beta is filled with giants of computer science, and understanding the algorithm will illuminate why Bird's derivation is so elegant. Here are a few highlights from the history of the alpha-beta algorithm. It appears that the idea was reinvented several times. Claude Shannon, in his 1950 paper on programming a computer to play chess, described a form of selective search. John McCarthy mentioned a similar idea at the Dartmouth Conference in 1956, calling it an approximation. Then in 1975, Knuth and Moore presented a paper on the analysis of the algorithm. The terminology they introduced is still used today. In 1982, Judea Pearl provided a runtime analysis showing that alpha-beta is asymptotically optimal for game trees. In 1987, Bird and Hughes derived the algorithm from first principles using program transformation and higher order functions. In 2002, Ginsberg and Jaffrey extended the method to distributive lattices, allowing it to handle games with partial information, such as bridge, and in 2024, Tobias Nipkow verified the algorithm in Isabelle. Looking at the history of this algorithm feels like walking through a hall of fame. We have giants here, and I count at least 2 Turing Award winners. It's a genuine joy to trace these ideas back to their roots. Dear viewer, if you're aiming to win a Turing Award one day, do me a favor, write your thesis on AlphaBeta. I would love a reason to come back and do a sequel to this video. Consider this position, taken from leechess.org. It is black to move. It is a very simple position. Please feel free to pause the video and work out the next move for yourself. We will use this tiny example to understand how the alpha-beta algorithm behaves. Step by step, when we look at the game tree, for even this very simple position, we see that it is still surprisingly large. Black can choose between pushing the pawn or selecting one of several king moves. And for each of those moves, white has a similar range of replies. Even at just 2 plies, the branching factor creates a tree with dozens of nodes. This is the kind of situation where alpha-beta pruning shines. It lets us avoid exploring large parts of this tree without changing the final evaluation. This tree on the screen shows a snapshot of how Stockfish views the position during analysis. The parallelogram-shaped nodes are the ones Stockfish decided are not worth exploring any further. Those subtrees have been pruned. They cannot influence the final evaluation, so the engine skips them. The best move from any position is determined by choosing the option that maximizes the player's score, no matter how the opponent replies. And at the next level, the opponent tries to minimize that score. So the evaluation alternates between maximizing and minimizing steps as we move down the tree. In this example, Stockfish has identified the best move for black to be pushing the pawn, and the best reply for white is to push its own pawn in return. This tiny position already shows the power of alpha-beta pruning. Even shallow trees contain many branches that do not need to be explored. This chess engine is a marvel of engineering, but it stands on a mountain of research. It is a hierarchy of insights where each breakthrough supports the next. To formalize this in Agda, we're going to step away from the chessboard and look at the formal rules that govern this kind of hierarchy. As Ginsberg and Jaffrey showed, these rules apply to chess, to bridge, and far beyond. They describe the structure of information, the structure of uncertainty, and the structure of choice. It is time to meet the lattice. A lattice is a hierarchy. Pick any 2 elements, and you can always look up to find their most specific common ancestor. And you can always look down to find their most general common descendant. Formally, a lattice is a partially ordered set in which every pair of elements A and B has 2 special values. The first is the least upper bound, also called the supremum or the join. It is written as A or B. It is the smallest element, that is greater than or equal to both A and B. The second is the greatest lower bound, also called the infimum or the meat. It is written as A and B. It is the largest element that is less than or equal to both A and B. Both operations, join and meet, must satisfy commutativity, associativity, and the absorption laws. A first approximation of the definition of a lattice is shown on the screen. Let us look at a few examples. Imagine the set of all subsets of the set containing A, B, and C. The ordering here is subset inclusion. The meet of two subsets is their intersection. The join of two subsets is their union. If you take any two subsets, their join is simply the set containing everything that appears in either, and their meet is the set containing only what appears in both. The top of this lattice is the full set AB. The bottom is the empty set. This power set forms a perfect example of a finite lattice. Here's another example. This time, we look at the natural numbers, ordered by divisibility. Under this ordering, 2 divides 6, so they are related. The meet in this structure is the greatest common divisor. The join is the least common multiple. Every pair of natural numbers has a unique GCD and a unique LCM. So this structure also forms a lattice. On the screen, you see the Hasse diagram of the divisors of 60. It is a beautiful example of how arithmetic naturally forms a lattice. As a final example, consider a set of pairs of numbers. The first component represents a heuristic score. The second component represents our confidence. In that score, the ordering works like this. A move X is strictly worse than a move Y, only if both components of X are less than or equal to the corresponding components of Y. So the comparison is done component-wise, and it is strict only when both dimensions agree. The join of two pairs is formed by taking the maximum of each component. The meet is formed by taking the minimum of each component. This gives us a lattice where every pair of evaluations has a unique best common upper bound and a unique best common lower bound. It is a simple structure, but it captures the idea that a move can be better in one dimension and worse in another, and the lattice keeps the bookkeeping clean. A distributive lattice is simply a lattice where join distributes over meet and meet distributes over join. These extra laws ensure that the structure behaves algebraically, like arithmetic on sets, or like logical conjunction and disjunction. The definition from the standard library is shown on the screen. It states that we begin with a lattice and then require two distribution properties. Join distributes over meet, and meet distributes over join. This gives us a very well-behaved structure, one that supports elegant reasoning and powerful program transformations. Let us add a little more structure to align with the framework used by Ginsberg and Jaffrey. We start with a distributive lattice. Now we require that it also has a single maximum element and a single minimum element. There is a top element such that every other element is less than or equal to it. And there is a bottom element, I hate that such that every element is greater than or equal to it. These two elements anchor the lattice. They give us a guaranteed ceiling and a guaranteed floor. This turns the structure into a bounded distributive lattice. On the screen, we see corresponding definition. Now that we have our lattices in hand, let us go and build our game tree. Here is a simple definition in Agda. It is parameterized over a type A. The tree has two constructors, a leaf, which holds a value of type A, and a node, which holds a list of subtrees. This is the basic structure from which all game trees are built. Leaves represent terminal positions. Nodes represent positions where a player must choose from a list of possible moves. On the screen, you see the Agda definition. Let us now define max, min, and min, max for our game tree. These are mutually recursive functions. Together, they form the executable specification of the two-player evaluation process. The function max-min is used for the first player. At a leaf, it simply returns the value. At a node, it chooses the maximum over all the children, but it does so by calling the minimizer. The function min-max is used for the opponent. At a leaf, it also returns the value. At a node, it chooses the minimum over all the children, but it does so by calling the maximizer. The helper functions maxes and mins handle lists of subtrees. For an empty list, max returns the bottom element, and mins returns the top element. For a non-empty list, they combine the recursive result, using join for maximization and meet for minimization. Both functions ultimately return the value stored at the leaves. The alternation between join and meet captures the alternating choices of the two players. Before we look at an optimal solution, let us introduce one more refinement. Engines like Stockfish use a variant called negamax. In this variant, a single function is used instead of separate max-min and min-max functions. The trick is simple. We flip the sign of the evaluation as we alternate between players. This symmetry allows Stockfish to use efficient caching, and it gives a clean, uniform structure to the alpha-beta window. To support this, in Agda, we need to add more structure to our bounded distributive lattice. Specifically, we require the lattice to satisfy the laws of a De Morgan algebra. The type must support a unary negation operator. This operator must be involutive. Negating twice returns the original value. The negation of top must be bottom, and the negation of bottom must be top. And finally, the De Morgan laws must hold. Negation turns joins into meets, and meets into joins. With this extra structure on our type, we can now define the negative tree. The idea is simple. We walk down the game tree, and at every alternate level, we flip the sign of the evaluation. This mirrors the alternation between maximizing and minimizing steps. In the original min-max formulation, the following mutually recursive functions capture this structure. At a leaf, We either keep the value as is or apply negation, depending on the current polarity. At a node, we recursively negate the children, flipping the polarity as we descend. This gives us a tree, where the sign alternates level by level, matching the behavior of the negamax algorithm. We can now define the specification of negamax, a single function that captures both min-max and max-min. The structure mirrors the negative tree we introduced just a moment ago. At a leaf, we return the value. At a node, we evaluate each child, flip its sign, and take the join. This corresponds to choosing the move that maximizes the negated score, which is the negamax principle. The helper function handles lists of subtrees. For an empty list, it returns the bottom element. For a non-empty list, it negates the recursive result and joins it with the rest. This compact definition encodes the entire alternating structure of two-player evaluation in a single, elegant function. Now we come to the alpha-beta definition. For negamax, this pair of mutually recursive functions implements alpha-beta pruning for a negamax evaluator parameterized by a window alpha and beta. At a leaf, we simply clamp the value to the interval between A and B. This mirrors the idea that anything below alpha or above beta cannot influence the final choice. The helper function handles lists of subtrees. For an empty list, we return the lower bound, A. For a non-empty list, we evaluate the first subtree using a negated window. This is the negamax symmetry. We flip the signs and swap the bounds. Once we compute the value of the first child, we join it with the current lower bound. If this new value is greater than B, we can safely prune the rest of the forest. To check this, we test whether joining the value with B leaves it unchanged. If it does, we have exceeded the window and no further exploration is needed. This is the heart of alpha-beta pruning. We avoid exploring branches that cannot affect the final result. We can now state a few key properties of negamax and alpha-beta negamax. I will only state the theorems here. The full proofs are available in the code linked in the description. The first lemma says this: if we run alpha-beta negamax with bounds A and B on a tree, the result is same as the value of negamax on the tree when clamped to the interval between A and B. The second lemma shows the behavior at the extremes. If we use the full window from bottom to top, alpha-beta negamax is identical to plain negamax. And finally, if we collapse the window so that A equals B, the output is just this corresponds to the fast left fold case described by Bird. Returning to Bird's paper, he derived alpha-beta pruning for a special case of trees of depth 2. But even in that restricted setting, you can clearly see how his function captures the essence of alpha-beta. We have covered a lot of ground in this video. We began with Bird's fusion laws and saw how they give us a principled way to reason about program transformations. From there, we stepped into the broader literature on alpha-beta pruning and compared the behavior of a naive game tree with the highly optimized structure used by engines like Stockfish. To understand why these optimizations work, we took a brief detour into lattice theory. We introduced lattices, distributive lattices, bounded lattices, and finally, De Morgan algebras. Each layer added just enough structure to support the algorithms that followed. With that foundation in place, we built the min-max evaluator, then the negamax variant, and finally, the AlphaBeta negamax algorithm that runs efficiently inside a window. This gave us a clean, executable specification that matches the behavior of real-world chess engines. It has been a long video and a dense one. If you want to explore the details, all the code, proofs, and references to the original papers are linked in the description. Thank you for staying with me through this deep dive. I hope it gives you a clearer view of the beautiful algebra that sits beneath modern game-playing engines.